Hello everyone, I am Abdelhak Bentaleb, CTO of Atlas Stream Company as well as a research fellow at National University of Singapore. My talk is entitled Adaptation Algorithm for Multi-CDN Parallel Strategy. First, let me give a brief introduction of Atlas Stream. Atlas Stream is a Singapore-based startup that works with the current video streaming standard by providing client-based solutions in the form of API and SDK to video on demand and live streaming services to power modern OTT video infrastructure. As shown in this figure, Atlas Stream solution sits on the top of any video player, helping player and content providers to deliver the highest possible quality of experience to end users video streaming with lower latency and cost. At Atlas Stream, we developed two solutions for the OTT video player and content providers. For VOD, we developed a multi-server dash video player API with smart load balancing that increased the quality of experience by 50%, reduced the CDN cost by 25%. For live, we developed CMOF-enabled dash video player API that reduces the video latency for your customer to 1 to 3 seconds, 30 to 50% better quality with smart and robust bandwidth estimation, and 25 cost saving. Current video streaming solution allows to use only one CDN at a time and use a third-party component or on-premise solution acting as a load balancer to switch between existing CDNs in case of server bottleneck. In this case, the player downloads the segment sequentially from the server. Although these solutions show good performance to some extent, they suffered from three main issues that directly contribute to unpleasant quality of experience. First, how to detect and avoid a bottleneck server in real time in order to reduce rebuffering events. Second, how to fully benefit and utilize existing CDNs for better video quality. Third, how to provide a fair quality distribution among clients using the same paid service. Here, the client that share an overloaded server or a bottleneck link limit themselves to a lower representation level to avoid playback stalls. Conversely, or in contrast, the clients on less loaded servers can achieve a much higher video quality, causing unfairness in the quality of experience. Solution of these issues is to use multiple CDNs in parallel. This will allow to benefit from heterogeneous CDNs from multiple vendors with different capacities and multipath capabilities, which includes aggregate bandwidth from multiple paths, fault tolerance, as well as robustness through path diversity. At Atlas Stream, we take this approach and develop a parallel multi-CDN solution that's based on a queuing theory approach. Atlas Stream solution leverages the availability of multiple CDNs by downloading segments in parallel. At Nutshell, the developed parallel multi-CDN solution uses a MXD1K queuing theory-based bitrate selection in conjunction with a request scheduler to download subsequent segments of the same quality through parallel requests to reduce quality fluctuations. It facilitates the aggregation of bandwidth from different servers and increases fault tolerance and robustness through path diversity. The resulting resilience prevents clients from suffering queue degradations when some of the CDNs become congested. It also helps to fully utilize the aggregated bandwidth from the servers and download the immediately required segment from the server with the highest throughput. As shown in the following example, the player that uses Atlas Stream solution is able to get up to 6 Mbps quality without any stall. In contrast to the player that uses only one CDN at a time will get only 1.5 Mbps, and the mentioned problems in the previous slides will be more aggravated in case of ultra high definition content. Atlas Stream Parallel Multi-CDN solution provides for content and player providers higher retention of customers without any additional costs and more than 20% CDN cost saving, automatic and dynamic CDN selection. For end users, more than 50% video quality, less rebuffering events, and high quality stability. The essential Atlas Stream Parallel Multi-CDN solution is to maximize the user satisfaction while playing video at the highest possible quality, avoiding rebuffering, frequent changes in quality, and long startup delays. It does not need any modifications in the CDN encoding content or the network. It works with any existing HTTP adaptive streaming setup. All modifications are performed in the player. Any player can enjoy Atlas Stream Parallel Multi-CDN capabilities with easy and minimal integration efforts. This figure shows player structure and the required modifications. It consists of four main entities. The first one is the player controller that monitors the playback buffer occupancy. The throughput estimator, which considers the last throughput from the individual server as its predicted future value of the throughput. The ABR controller uses a queue-based model to decide the bitrate level for the next segment to be downloaded. Finally, the scheduler controller requests and downloads the segments from the appropriate server. Here, the player requires only to know available CDNs that should be included in the manifest. For example, for Dash, we have to use the base URL tag of the MPD file to list all the available CDNs. During Atlas Stream multi-CDN solution design, we take care of the following rules. Accurate throughput measurements from different CDNs. While downloading segments in parallel from multiple servers, it's important to ensure that not more than one segment is downloaded from a server, otherwise multiple segments downloads would be competing against each other and results in wrong measurements. Parallel requests for multiple segments. To leverage the aggregate bandwidth from all the servers, the client must request different segments from different servers. Our solution averts the duplicate download of a segment to avoid resource wastage. The third one is the buffer overflow and underflow prevention. The scheduler must keep track of current buffer level before sending a segment request. First, to avoid exceeding the buffer capacity, once the maximum buffer is reached, the scheduler reduces the number of servers gradually until it reaches 1. Second, to avoid buffer underflow, once current buffer is less than defined minimum buffer, then the scheduler is expected to send a segment request to all the servers. The fourth point is identification of the bottleneck server. If the download throughput of the last segment is less than the lowest available bitrate, which might harm the QE, then refrain from requesting a new segments from this CDN until it becomes healthier. So as I mentioned before, our solution uses queuing theory to select the best possible bitrate level while maintaining optimum buffer occupancy level subjected to download throughput from different servers, available ABR ladder, current buffer occupancy, and total buffer capacity for maximizing the quality of experience. Therefore, as depicted in this figure, the ABR works as follows. The arrival rate denoted by lambda of segments from different servers are modeled as a batch process. Then it calculates the total effective arrival rate by summing the individual rates lambda m from each server SM. The segments in the same batch are downloaded at the same bitrate level. Then the ABR selection considers the aggregate arrival rates from different servers. To evaluate the robustness of Atlas Stream multi-CDN solution, we performed extensive video-on-demand tests with different scenarios. We used 5 network fluctuation profiles, P1 to P5 from -IF guidelines, as shown in this table. CDN that runs P3 is the bottleneck server. For the content, we used Big Bag Bunny with 10 minutes duration, various segment durations, and maximum buffer configurations. For 1 second segment duration, we used 30-second maximum buffer. For 2 second segments duration, we used 6 second maximum buffer, and so on. The APR ladder consists of 9 bitrate level and 6 resolutions. This is given by distributed Dash dataset from Klagenfurt University. We compare our solution against single source one-to-one, where each player can download segments only from a single CDN, and the 4 CDN-based load balancing rules that are implemented in industry. The first one is round robin. The set of requests to the CDNs are distributed based on a round robin mechanism. The second one is least connected. The next requests are assigned to the CDNs with a lower load. Thus, this scheme tries not to overload a busy CDN with too many requests. The third one is session persistence. It always directs a request from the same client to the same CDN using a hash table, except when this server is down, and the last one is weighted. So here the weights are used to influence the load balancer to give preference to servers with a higher weights. For example, if there are 3 servers and the first one has a weight of 3, while the other 2 have the default weights, then out of 5 new requests, the first server will receive 3 requests, while the other 2 servers will get 1 request each. Other configurations are listed in this slide. So for the QE, we use the following weighted linear QE model that combines 4 metrics: the average quality switches, rebuffering duration, and startup delay. So delta 1 and delta 2 is fixed to 1, and delta 3 and delta 4 is fixed to the maximum bitrate level. In the first test, we analyzed the scenario where one client requests video segments from a single CDN for 5 different network profiles, P1 to P5. Then we compared it to the case where 5 different clients are requesting video segments from all the 5 CDNs with the network profiles P1 to P5 respectively. The idea is to compare the performance of one-to-one client CDN for 5 clients with respect to all clients using all CDNs using the Atlas Stream Parallel Multi-CDN solution. These figures show the average bitrate played left and the number of bitrate switches right during the entire session. Atlas Stream clients achieves better average bitrate of 3.9 to 4 Mbps and less number of switches of 2 to 13 for different maximum buffer capacities compared to one-to-one client. For the same test, these graphs show stall duration versus number of stalls left and the quality of experience, the right graph, that's experienced by different clients. So a high quality, less switches and 0 stalls translates to higher QE achieved by Atlas Stream clients compared to one-to-one clients. Atlas Stream clients outperform as one-to-one clients by 4 to 33% on average in terms of QE for different maximum buffer configuration. In the second test, we compared Atlas Stream Parallel Multi-CDN solution against CDN-based load balancing rules that are implemented in the industry. So we ran 5 CDNs with 5 different network profiles, P1 to P5, shared by 5 concurrent clients. So each profile is used to shape the total capacity between a CDN and the set of clients. So left graph depicts the average bitrate played during the video streaming session. In all maximum buffer capacity configurations, we can see that Atlas Stream players achieve the best and the most stable average bitrate that ranges from 3.9 Mbps to 4 Mbps compared to CDN-based load balancing rules. Further, Atlas Stream solution is able to ensure fairness in terms of the average bitrate among all clients with a variation of 0.1 Mbps, 0.15 Mbps, and 0.3 Mbps for 30-second, 60-second, and 120-second maximum buffer capacities respectively. Similar outcomes are achieved by Atlas Stream clients in terms of number of bitrate switches with an average of 2 to 10 for different buffer capacities. So for the same test, the left graph shows the stall duration versus number of stalls, and the right graph shows the QE achieved by all the players for different maximum buffer configurations. The CDN least connected applies an efficient request strategy that distributes requests of clients across CDNs according to their capacities. This strategy sends the request to the powerful server, which executes requests more quickly and alleviates the adverse effect of bottleneck server. However, the CDN persistent creates a fixed association based on the hash value between a client and the CDN, where all the requests from a given hash value are always forwarded to the same CDN. Thus, the client attached to the bottleneck server will receive a low bitrate, and this affects the average results over all clients. The Atlas Stream solution, in contrast to the CDN-based load balancing rules, leverages all existing CDN servers and downloads segments from all of them in parallel. It successfully detects a bottleneck server via a smart bottleneck detection strategy thus it avoids to test the scalability of Atlas Stream parallel multi-CDN solution in constrained network. We run 100 clients over Google Chrome with 4 CDNs with profiles 60, 70, 80, and 90 megabyte per second respectively. For the weighted load balancing rule, the 4 CDNs are associated with the weights 1, 2, 3, and 4 respectively. So the results of this test is depicted in this figure. So left plot is the average played bit rates, middle plot is the number of switches, and the right plot is the quality of experience for different maximum buffer capacities. So Atlas Stream solution is able to achieve significant improvement in the quality of experience of 10 to 70% with a high bitrate without rebufferings and less quality switches for all maximum buffer capacities compared to CDN load balancing rules. This video shows the demo of Atlas Stream parallel multi-CDN solution. As we can see, Atlas Stream player top left connect to 3 servers, achieves better and stable quality with less startup delay and without stalls compared to the 3 players connected to server 1, server 2, and server 3 one-to-one respectively. You can test Atlas Stream parallel multi-CDN solution with your content using our demo page. The second solution of Atlas Stream is low latency live streaming with CMOF enabled. Atlas Stream low latency live streaming solution provides many benefits. For content and player providers, high retention of customers, no additional cost, and easier and faster integration. For the user, it provides low latency in a range of 1 to 3 seconds, high quality with accurate throughput measurements, and less rebuffering. This is the demo of Atlas Stream low latency live streaming compared to one of the existing commercial solutions. You can see clearly that the player that uses Atlas Stream solution achieves better quality as well as low latency. Also, you can test your content by visiting our demo page on our websites. You can test Atlas Stream parallel multi-CDN solution with your content using our demo page. This some of our records and recognitions. This our team. Thank you.